Welcome to Module 4.1, Grids Balancing Through Space. This is the first of the three ways to deal with variability that we will look at. The goal is simple. We are trying to get the variable renewable generation time series closer to the demand time series. In a little drawing, I have indicated this with the dotted and the solid orange line. We are trying to move the dotted line so it looks more like the solid line, which is closer to the gray demand line. This is actually quite simple. The further away 2 points on the planet are from each other, the less correlated their weather is. So I might have a wind farm in Germany and its electricity generation profile, a time series again, over say a day or so, looks something like what you see here. If I have a second wind farm quite close to the first one, let's say in the Netherlands, its electricity generation profile over this day might look quite similar. But if I move further away, say to the southernmost point of Portugal on the Atlantic coast, the electricity generation profile will look quite different from the other two. So, in simplified terms, by spreading out my wind farms in space, I can exploit the fact that it's almost always windy somewhere. We can make this more concrete. Here I have simulated the actual 1 hour average capacity factor of a single wind power plant in Bremen, Germany, over the course of 5 days in March 2019, based on the actual weather conditions during those days. You can see that the hourly capacity factor, and thus the electricity generated, fluctuates quite dramatically. So let's simulate the combined electricity generation from all wind farms in Germany for the same time period. You can see that the generation profile is already a lot smoother. And we can go further and simulate all wind farms across Europe for the same time period. Again, the overall generation profile is much smoother. The same is the case for PV. Here, I am comparing the simulated output from a single rooftop PV system in the city of Milan with the total PV electricity generation from all of Italy over the year 2015. Showing you average daily capacity factors. You can see that the single site in Milan sometimes suffers from very cloudy days, even in summer, producing almost no electricity at all, with a daily capacity factor near zero. But the country as a whole has a much smoother generation profile. There's a lot of research around the world on better understanding and forecasting the variability of renewable generation. Better understanding of these spatial patterns of variability could already be taken into consideration in the planning stage. For example, when deciding where to build new wind farms. Here in black, you see a simulation of the 5-day average electricity generation from all of Europe's wind farms over December, January, and February. In red, the electricity generation from all existing and future wind farms, if those additional wind farms are mostly built in the North Sea area. Which makes sense because that is one of the windiest areas. So the owners of those wind farms will be able to sell more electricity and thus make more money. But the extent of fluctuations goes up dramatically, as you can see here in the red line. Of course, since as we said, the further apart in space you are, the less correlation there is. If you put everything in one spot, there's a lot of correlation. In other words, all those wind farms in the North Sea behave the same way. An alternative would be to distribute this new wind farm capacity to other parts of Europe, exploiting the fact that these areas are far away from each other, with the resulting electricity generation profile shown here in blue. As you can see, this keeps the overall variability of Europe's wind generation fleet similar to what it already is today. However, there's a considerable problem here. If we distribute our electricity generation infrastructure in space, we may also need more power lines to move this electricity around. For example, if Portugal has a massive overproduction of wind electricity, while Northern Europe has little or no wind, that electricity would need to be transported from Portugal to Northern Europe. It is possible to solve this problem by building dedicated power lines. For example, high voltage direct current lines, HVDC, which do not lose as much electricity along the way as the regular high voltage lines you generally see in the landscape. China is doing this, for example, in simplified terms. There are very sunny and windy parts of the country, but they are not where people live. So dedicated HVDC power lines bring the electricity to where it is needed. The distances, however, are large, and in densely populated areas, building new power lines is difficult. And some variability problems remain in any case, like seasonal variability. It's winter everywhere in Europe at the same time, and everywhere in China at the same time. So, geographical balancing can be part of the solution, but it alone does not solve the problem. And that is why we will look at a really critical option next: storage.